we don't have a discussion today. Then we can have a longer lecture. Or you can raise your questions. Right? Because we already sent our lecture material, then you should read it before coming and raise questions. That is our new education 4.0. No lecture, only discussion.
교수님, 오늘 아비 학생이 그 연구실 세미나 때문에 오늘 수업 바꾼 걸로 알고 있는데 혹시는
그래서 못 온다고요?
네, 그래서 오늘 수업 바꾼 걸로 알고 있습니다.
그럼 다음 부분?
네.
Okay. We can start. Right. So today, Mutahar will start on chapter 7. And myself. So we can use, say, 30 minutes? Enough time, right? Yes. Including discussion. So your mission is to raise this discussion during the lecture, right?
Hi everyone, good afternoon. I'm Mutahar. I will start the 7th chapter today. Chapter name is actually Feature Mapping and Data Exchange. Here I have just written the feature mapping. This is the reference book, and we are now ending the part 3 of the book with the chapter 7th. So these are the contents which I will be covering today: feature mapping, and in feature mapping, feature classes and different feature techniques. Sorry. Okay. These are the details of my contents. In feature mapping, there are a lot of new feature classes which I am going to introduce today. And later on, the feature mapping techniques through which we can actually map the feature between different systems, for example, between design and manufacturing system. So the the reason why we need to map features is that no matter whether we use the traditional concepts during the product life cycle, which was the sequential engineering, like one task was completed and then the other was started. But recently there is this concurrent engineering to save the time, as you can see. But in both the cases, we need the sharing of product data, which means that if the system is feature-based system, then we need to map the features from one system to the other. As we saw in the third chapter, that features are viewpoint dependent, which means that intended application actually defines how you want to look at the same part, but the feature can be different. For example, we can look at this part from design viewpoint, from machining viewpoint, from inspection, as well as from the deburring, and there can be more. So this is actually the actual complication, that when we are viewing the same part from different point of views, so we need to take care of this fact during the mapping, like I will discuss later on. So one of the example of the mapping can be from the design system to manufacturing system. Design system was can have the features defined as the stereotypical shapes related to parts function, and manufacturing system can define the same shapes as that are possible with the manufacturing processes. So we need to go from the function viewpoint to the available manufacturing operation. And secondly, you may raise the question that what is the difference between feature recognition and feature mapping? In feature recognition, we had the original geometric model, and we started with that, and we didn't use any previously available viewpoint. So we picked the entities or used any method, so we defined from the zero. There was no other previous defined features. But in feature mapping, user derives task specific or viewpoint specific feature from existing feature model. So if you had the design system, so the features that were defined in the design system that are used to get the features of the manufacturing system. So the input here is the feature model. Input in the feature recognition was the geometric model. Okay, I added this one after going through the book. In book, he's saying that just like I hope everyone has studied the linear algebra. In linear algebra, we have vector space, and vector space is not something a physical space, but a space which is closed over some operations. And one of the thing is that you can be sure of the different possible cases, like it won't go out of that space, so it is closed, and let's say addition and scalar multiplication. Similarly, he defined feature space, and he said that product type, application, and level of detail or level of abstraction can act as the basis vectors, and we can define a feature hyperspace, which is for all the possible cases throughout the product life cycle. So when we have one feature, it is actually the subspace of that feature hyperspace. And then, as we know that the spaces individually and together, they can have different relations. And today's discussion about the feature classes and feature techniques is taking the conjugate class, which conjugate space, which I will define in the next slide. So whatever I will introduce in the later lecture, it is considering the conjugate space of the feature hyperspace. Mapping classes. First, there are different mapping classes, and he is saying that several common situations that arise in transforming feature model between conjugate spaces are defined as mapping classes. So conjugate spaces actually are the spaces which are completely dependent on the user viewpoint, something related with the actual definition of the feature, like the elements are going to remain the same, only the viewpoint is going to change. For example, I added this picture here of a part. One user can say there are 5 ribs, but the other can say there are 12 pockets. So if you take out one rib, the number of pockets will change. So in either case, either you are defining it with the number of the ribs or number of the pockets, it is the same part with the same number, same elements. So that is the conjugate space. So first type of mapping classes is one-to-one mapping. It is the simplest case. Features like holes, pockets, slots, and ribs may be similarly defined in the both systems, the source system and the target system. So the definition base can be the same, and it is possible that it can have different name. For example, I have this example here. One system can say that when you extrude a profile, it names it pad. The other can name it extrude. The other can name it protrusion. But the way how it is defined, this feature is the same. That is one profile, and you add a volume to this one. So when we want to take such kind of feature to the other feature, this is something like easy, you can know. So the next is the variant re-parametrization. Variant re-parametrization is something when the different, actually when everything like the name and other are the same, but the parameters in their amount have been different. One example he used is the references system can be different, can be either local reference system or global reference system. So design feature that map directly into process planning features have been parameterized in different ways and positioned using different reference systems. So the values are changed in the magnitude, and the reference system can be same, but they have the ability to directly map with the process. So how we can map? We can add the equations that take the input and processes those, and that give the output in the process planning or machining features. So this is the way how these features are mapped. So one example here is the global and local, so we know that we can change in between. The third type of the feature classes is this specialization mapping. When level of specializations of two sets of features are different, geometry or parameterization can be the same. Like the previous example was different parameterization. And example here is this hole, which is a design feature. We know it has a cylindrical face, bottom flat face, simple hole. It can be manufactured by either of the systems given here. But each system has its own way to define the whole feature as it is. But as you see that A and B are the general, but C and D are the special processes that are there to just make the holes. So the amount of information required for by these systems to identify a designed whole feature will be different. So it means that one whole feature from one design system can go to all these 4 and maybe more systems. So it is kind of one-to-one mapping. Next type of the mapping classes is the generalization mapping. It is the inverse of the previous type, which was specialization mapping. What is happening here is that more different detailed features are all mapped to single more abstract entity. So this means that you are coming from more detail to low detail. So it can be like projection of a vector in 3D to a 2D plane. So you lose or you give away some part of the information. Example here is that if you are a packaging designer and making this what is it called? No, the like
PCB.
Yes. Yes, PCB circuit board. So packaging designer deals with the actual components, but the electronic designer who drew the drawing, for him it's this is just a rectangle. He will just make it on the paper, but the actual who is making this PCB circuit board, he will deal with the actual components. So there can be many different components who can fit into it. So many different type of the this PCB circuit boards can have the same 2D drawing. So you can have the idea it is N-to-1 mapping. The next type of the mapping classes is discrete aggregation. Discrete aggregation is actually when more than one features in the source system which can be designed is combined into a single. So aggregation decision on which basis you are combining the feature is dependent on the process planning or on the decision of the process planner, if you are the process planner. So generally you can make a universal rule. The video that I shared yesterday, in which the user was defining the rules, how you will map. So that is actually the universal rule is included in the mapping program that operates on the selected feature sets. Here the example you can see one pocket is actually the bigger one, and the slot, they are combined into the milled pocket. So milled pocket is one machine feature. Discrete decomposition. Again, it is inverse of the discrete aggregation. Here one feature, depending on the ease of machining or manufacturability, is decomposed into more than one feature. So discrete decomposition is also dependent on the process planner's decision. For example, if we have a counterboard hole, its manufacturing sequence can be that first you make the you don't make it as it is, but you decompose it into two machining features. One is the blind hole, the longer one, and then you widen the opening at the top. So you make it in two steps. Last of the mapping classes is this conjugate mapping. In conjugate mapping, it is actually they are saying the most complex case of mapping classes. Features are broken down into their constituent faces. So everything is decomposed in terms of the faces. Faces are again regrouped. Something again which is depending on the process planner's decision. Like if he is easy with the three faces which can be manufacturing by a non-machining operation. So there is not 1 to n or n to 1. It is m number of features to new n features. So conjugate mapping is used when some manufacturing features are missing. So it is better to decompose all the design features into the faces, and then faces are combined in a way that the resulting machining features are all manufacturable. One example can be like that. Next, my topic for today is the mapping techniques, how we can actually map from one system to the other system. And these techniques which I am going to discuss are mostly dealing with in between the design system and the manufacturing system. And but before that, he is saying that in the book that there are some method. through which we can avoid feature mapping if we don't use feature. So we already have the idea that before features we used to have the geometric models, but and in the last lecture we learned about destructive solid geometry, and there is domain dependent, like a feature recognizer that is specially for one type of domain. But in both these cases, the problem is that there are such methods which are dependent on the geometric model. So their input is geometric, they have low information. So again, we are forced to move to the features, or features are better because they have more information. So the 4 mapping techniques which I'm going to cover today are these: heuristic methods, intermediate level structures, and the last 2 we already have some idea in the feature recognition lab. We deal with the cell-based and also graph-based. But as I told you, that feature recognition is little bit different from feature mapping. So the heuristic method, actually heuristic is any approach to problem solving that is not dependent on the exact some engineering rule, but it is sufficient for reaching at the desired or immediate goal. So if you can also propose some method which you can claim that okay, this will solve this, but it doesn't have any engineering basis. So that methods can be called as heuristic methods. First one is this proposed by Chamberlain in 1993. So it is considering only the negative and positive features. I think they are solids or voids kind of. So designer expresses the part in terms of negative depression features and positive protrusion features. Once he has done this, so he finds 2 type of feature. One that are directly mappable with the manufacturing, so that are no problem, you can map them, and the remaining one is where you apply the actually heuristic method. So heuristic approach here is that those which are not directly mappable, you convert them into a BREP, which is then used as an input to a feature recognizer. So here a feature recognizer is used. So which feature recognize start from, let's say, one face, add the face, and workpiece is something that can be translated into a manufacturing feature. So when such a combination of the BREP element is achieved, which is translated to the manufacturing feature, the recognizer stops, so you have one machining feature. So you apply this again and again until all the other which were not directly mappable are now in the form of machine. So this part is actually heuristic. Second was proposed by Xiao, 1990. So something like, he said, database, like extensible feature system for mapping only this case of design feature with manufacturing feature. And he said that we can have such a database where both documented and undocumented features can be stored in advance. So documented was that which are known to the application program, and undocumented features are those that application has no knowledge. So heuristic here is applied on the undocumented features. Again, similar to previous method, there is every feature set and a bounding box. Bounding box is taking the whole part inside, and the feature set is all the faces. So the faces, it means that you have to machine them. So you check their machinability, like is the tools, can the tool go there? So some machining conditions you compare with the faces, and then if it's okay, you add that face to a manufacturing tree. So in this way, here the heuristic method is applied. Second technique to the feature mapping is intermediate level structures. The proposer was Sri Kantappa and Crawford in 1992. Here the intermediate is actually something in between the geometry and the features. Like more information than the geometry, maybe less information than the features. So level of abstraction that lies between geometry and features consists of abstract geometric relationship. We know that the feature definition is actually a geometric shape that has some engineering significance. So engineering significance is added or packaged. So here the packaging certain geometric and topological relationships which change with the viewpoint. So intermediate geometry actually is a level of the model which have these relationships. So why relationships? Because let's say if one design feature is to be used by 10 different machining systems, so adding the detailed information of that 10 different machining feature, it is better to add relations which can be used to get that information, something of expressions or equations. So it is definitely less in magnitude. A processor determines the intermediate geometry from the feature model, which is input, and intermediate geometry is passed on to the application to ease the feature extraction. So features are then extracted from the intermediate geometry. The second method in the intermediate level structure is of that proposed by Goth in 1994. Here actually loop is something, if you look at the topological hierarchy of any geometric modeling kernel, loop is, I think, in between the faces and the edges. If we make all the connected edges, that is the loop. Same is here. The C loop is actually the loop of the edges. He is saying that defined as a concave or convex loops of edges used to characterize typical features such as depression. Somehow the loop can tell us whether it is a protrusion or it is a depression. So it is a grammar which helps in mapping of low level geometry to high level features. Next step involves feature recognition to get application specific features. He is saying that the feature mapping can be facilitated by using taxonomical coding scheme as an intermediate. So intermediate geometry can be standardized for one set of application between design and manufacturing. Next is that cell-based mapping. We also saw that in the automatic feature recognition we had one type of machining region recognition, and in machining region recognition we had this cell decomposition technique. Actually the decomposition here is the same, but the difference is that the volume decomposition here is also taking the advantage of some feature information in the input model as well. So that is not available in the feature recognition. We're starting from the zero in the feature recognition. Here some of the information of already existing features is also used when we are decompose the model in the cells. So volumes are combined into different, so this actually first line is actually once we have the cells. So first we make the cells. Cell can either be a solid or a void. So there are different methods for making the cells, but all of those methods, they have these 4 steps. First step is that determine volume to be removed. So by machining as the raw stock minus the finished. As you can see in this in this diagram, we need to make this kind of hole, different than hole anyhow. So what we do is that second step is that the material to be removed is partitioned, each material removal volume into some elementary sub-volume. So the hole which need to be removed is further decomposed. The next step is that combine the elementary volume into machine. Now you have the freedom. So depending on your manufacturing system or manufacturability options, you can then combine them into the different, so he has shown different possible arrangements. Last is that once you have combined them, match machinable features to machining operations on the basis of the above classification. So there are major contributors to these four phases. There was this, I will explain the last one, in which they gave the feature interaction option. So there is not a single method is not giving these four steps. The different methods are combined, and then these general four phases are made to have this cell-based mapping. So in this last one, they are giving the user interaction between the multiple interaction of the design model to get the manufacturing feature. For example, H1 is the hole to be removed, and H2 gives the H1 interaction with the S1. S1 is the upper slot, and H3 gives the hole interaction with the S2 second slot. H4 is the interaction of hole feature with the both of the slots. So you have the different interactions. Last is the graph-based mapping method. As we know from the feature recognition chapter, that one feature can be shown as its equivalent face adjacency graph, in which the feature is decomposed into faces, and the every node indicates the faces, and the connection in between the faces is the edges that is adjacent to them. So similar to that, features are subgraphs, same thing, that are isomorphic means similar to stereotypical subgraph like we use in other subjects. So feature mapping is that transition from one subgraph to other subgraph. So here the method was proposed by Falcidiano, I think, 1992, an application independent, neutral, feature oriented model from the common basis of possibly different application dependent models. So there are two types of node. One is the root node. Root node is the start point, and it is showing the actual shape, and the other nodes are either protrusions or depressions. So graph is kind of a grammar for feature representation. I took this example from the 9th chapter. You can see a slot is actually, pocket is actually shown by its representative face adjacency graph. So that's all from my side. Thank you.
Can you explain variational re-parametrization?
Yes. I think variational re-parametrization is that, let's say, our both design and machine manufacturing system have the one feature that is whole, so name is same, but the let's say the diameter and length is changed as like different ways and positioned using different reference system. So the name is same, but the input parameters which control the geometry are different. So we can have some expressions which can be used to get just change the parameter. Easy example is that some systems are using global coordinate and some, but we can move from one to the other. So in such case, the mapping is called variant re-parametrization. Any other question?
My question is that what is the difference between mapping class and mapping technique?
Mm-hmm.
Like mapping technique use several mapping classes?
Mapping classes are the different mapping cases like situations, different situations that you can feel in the practice, face in the practice when you are mapping, like one case, second case, third case.
Can I see the slide?
Actually, she is asking the difference between these two. The mapping classes are the different situations which we can face while we are mapping the features, and actually techniques are the available methods which we can use to solve those cases. So techniques are the methods and classes are the cases.
So, for mapping techniques cover the all of
All.
mapping classes?
Yes. Okay then.
All right. Mapping classes and mapping techniques looks similar to me, even to me. This is techniques. Number of techniques here, right? And class is also number of 7. But for me, it looks similar. But can we say it is more higher level classes, and then techniques are more low level, specific method. Both are, for me, method of mapping. Right. I want to explain one more. This one. Concurrent engineering. Why we need a feature in this case? Because what is the difference between sequential and concurrent? This is a time compression. So I want see CQT. CQT is a 3 main element for competitiveness, right? They want to reduce time here by using concurrent engineering. And I'm saying in this day that these are three important factors, but among them, in these days, not old days, time is most important for the competitiveness. 3 is still important, but among them, I can say time is most. That's why we need to reduce time to market by using many methods, but one of them is this one. But it's good to reduce time, but there is a problem of making in this way. Because here you say that the marketing department, design department, prototyping department, and manufacturing department, they are all separated in time series, right? So they have a good finish each segment and hand over to the next stage. Now, here they start before they finish their work. So there is a problem of that, say, they can change their mind, right? When they started already and work, but marketing team, they changed color. They can change some component. They can change some dimension. Then they should start again, right? Then it can create another delay. So it can be worse than this one. sometimes, right? If you do not have a good management skill. So here, you need to have a more better collaboration than before, because there are many things can be changed, right? So information flow is more important than before. You can reduce time, but you should manage better than before. And management, among them, communication is most important. For the communication, you need to have a information flow. So one of the information flow, I can say the database, so that they can be shared information through single database. So single information can be shared by many departments, so that they can reduce rework, they can reduce time, and among them you can use feature concept for more clear communication and separation of concept into feature. All right, my part. All right. And data exchange. I am trying to explain more about data exchange. And feature data exchange. And method, one of them is step. Right? Step is a ISO standard. And short name of them, one of them. So exchange, global marketplace, highly competitive, partnership, outsourcing, right. Because of one of the key reasons for outsourcing is they want to reduce risk. Risk is burden is going onto the supplier rather than holding myself. I want to be lean manufacturing, means my body can be smaller, so it can move quickly to a changing market. Less stock in the store. I may have a big storage of material, human, and devices, right? If I do myself all alone, then I need a big amount of resources. But if I outsourcing, then myself is smaller, right? And then when something is changed, I can change it easily without changing many resources. But burden is going to the vendors, the suppliers. But smaller suppliers, they also can be faster, so flexible to change to the market. Anyway, partnership, right? And fast also again, the communication is important between partners. So customers, partnership, partners, right? Subcontractors, suppliers, look similar, right? Look similar. But then anyway, they need to have a product data exchange. Correct, fast, and standard format. Otherwise, the communication can be worse than before. Product life cycle. This is a timeline. Feature data exchange involves a number of software technology and method. Translation, very similar to language translation. Google Translator, very similar. From one computer CAD system to another CAD file format. Right. Between partners, between subcontractors, between customer, also customer. Right. Customer, you say, it can be say GM Motors. It can be a buyer. So there is a layers, customer, subcontractor layers, right? So it can be in any chance. Myself here, there is a customer. I can be a part manufacturer, say, electric motor manufacturer. then customer can be a automaker or boiler maker or other, several, right? Several. Because I'm producing electric motors. Then I have a partners. They can provide material, bolt nut and wires, electrical wires and others, right? So between them, the information about ordering and also another ordering, right? Subcontracting and information, designs and other things should be shared. So for the feature data exchange, there should be similarity between two CAD systems. Right? If they are similar, it's easier. Between, I don't know, Germany or Italian and French is easier, right? Than Germany? Then Korean? Right. So similarity is different, right? Similarity. Same level of information, usually the level is similar. But if you go to the, say, 1,000 years ago, then the level of information can be different. There is a very special region so that small people are living there in same as 1,000 years ago. So they don't have a letter, they don't have clothes, they don't have car. So level of information is different, right? And also between, say, ourselves and children, say 5 years old, the level of information is different, right? So communication is not easy, right? Entities and semantics, right? Entities, the component, and semantics. Because 5 years old, they memorize only 1,000 words. We are using, how many we are using? Million? So also there is a direct and indirect translation. Language too, right? Google provides direct translation. But many times in, say, my younger age, we translate, Korean book makers translate Japan translation rather than original. Easier and cheaper. Say there is a new Nobel Prize poetry or book coming, and then Japan is very fast in, say, 20 years ago to translate and produce book. And Korean books makers, publishers, they have a small number of translators. They cannot translate Russian book directly because there is no translator. Then usually they can use Japanese book first. It's easier, and then modify. So indirect translation. But direct translation is usually better, right? And third party is another company. They are only specialized in translation. Right? So it's outsourcing of translation. Intermediate, there is indirect translation. So this is direct translation. It's Bangladesh, French, Pakistan, Korea, right? And then direct translation. It's better, but it takes more cost. You need to have more resource, much translators, more translators. But this is indirect translation. Russian, Japanese, and Korean. Or many times nowadays, English or French, right? Indirect translation. So two translations, so quality can be lower than direct translation. But it can be cheaper, it can be faster. So you need to have an advantage and disadvantage. And number of translators too. You see that, number of translators. You need to develop number of translators. Then, so between 100 nations or languages, right? translators can be 10,000. Okay, standard format IGS is an American standard. DXF is coming from AutoCAD company, so it's a commercial, but it's well known in the United States. But this is an ISO standard, so it's bold-faced. JT is coming Siemens, so another commercial. German national, very similar to these two, right? And Parasolid is also Siemens, but there is a special small company. Siemens bought that by that company, merged that company. Now Siemens. So ISO standard for the computer interpretable means computer can recognize, understand, right, the representation, the written document, step format, step file, and then exchange to industrial product data means you can say design data. But they are saying it's more than design data. It is saying product data. Design data is smaller. It's saying product data is bigger, but main part is design data. Right? More than design data. You can say product data. Official title of TC, Technical Committee is automation, industrial automation. And subcommittee of this technical committee is, one of them is subcommittee 4. They are handling product data, and that is the step. So history, it started in 1984. So more than 40 years now, right? More than 40 years. So they tried to upgrade IGS. This is from French. Very similar to Germany and DXF. This was the starting point, AutoCAD. Then trying to make this one, because it's commercial, they want to make a more neutral one. Independent, neutral means independent from commercial. Right? So United States, Germany, and French, SAT, they do their own national standard. So it was replacement DXF to national standard. And they extend. But these are usually 2D, because AutoCAD started from 2D DXF. Right? DXF is still 2D, I guess. But 3D then. And then now they are saying modular architecture. Modular means hardware, also this is software or standard. So modular architecture of standard, of step, modular application protocol. I explain a little bit more on this. And then they have modules. Each one is application modules. And then by combining application modules, you can have a big industrial application protocol. Before then, they used old architecture. They are saying current because it was 10 years ago. Now they already moved to here. So one AP is divided to 5 parts. Activity model, conformance classes, requirement model, mapping table, and interpreted model. Anyway, say application protocol for shipbuilding industry, application protocol for automotive industry, separate. For each industry or domain has a separate application protocol. They have an activity model, they have a requirement model, they have an interpreted model. And below them, there is a common resources. It's a component. But they want to make it be more modular component, or bigger component. Very similar to car design. Modular platform. I explained on Monday. Modular platform. Strengths, neutral. Neutral means, once again, neutral from commercial. Right? Neutral from commercial. You can raise any questions. Right? Otherwise, commercial. Neutral from commercial. Long-term archiving, say Airbus from France. How long it operates? 20 years? More than 20 years. There was an accident from Indonesia yesterday, but they are saying that it's a new airplane, not old one. But sometimes they have a very old airplanes, right? Still operating. Cars also, right? 20 years, more than 20 years, right? Still operating. Nuclear power plant, 40 years, 50 years operating, right? Then we have Koreans, we have a first nuclear power plant starting to dismantle. And that operated already 35 years already. Right. Then 35 years ago, what is the 35 years ago? 1980, right? 1980. They have only paper drawings. The nuclear power plant which trying to disassembly, right? But they need to have an analysis now, because it can be dangerous to disassemble. Open the radioactive assembly, right? So they want to make many analysis before disassembly. Radioactivity analysis, structural analysis, CFD, hydrodynamics, heat exchange, or many others, right? But the how can I say? The old drawings are not correct to the current situation, because there is many changes, small changes, not big changes, small changes, right? Small additions. Electronics almost different from 40 years ago, right? 35 years ago. Concrete may be similar, but old, 35 years before. Not new concrete, right? So that material is changed, material properties changed. So they need a new model, new drawings to represent the current situation based on old paper drawings. That is the first thing they need to do. And then they can start analysis. After analysis, they can start the operation of real disassembly, right? Long-term archiving. At that time, I guess there is no 3D CAD system. Only that's why they are paper drawing. Now they are building a new nuclear power plant, right? Under construction. They have a 3D CAD files, CAD modeling, right? Now, new construction. That nuclear power plant, after 50 years ago, later, after 50 years later, the CAD file can be opened for the new finite element analysis. You can guess that computer OS system can be totally different after 50 years. Not only the CAD system, the operating system. So you need to have open that file after 50 years. Otherwise, it's worse than having paper drawings. Right? There is a file, digital file. After 50 years, you cannot open that file. What can do that? Right? You can measure again the nuclear power plant. Right? That is why we need the standard. Standard is trying to show all the structure inside the file, right? Document it. you know what is the meaning of this segment or statement of file, step file. After 50 years old, you can understand. There may be no translator of current. There is a translator now, but after 50 years later, the translator can be totally different, right? Still, you can read that file by one, because there is a standard. This is important. Migration. Migration means you have a new version of operating system, Windows 10. What is the version now? 11, 12? Windows 10. Still 10? Still 10, right. But I have an old computer which is operating Windows 8. But files are there, so we call this as a migration, upgrading. We call it a migration. So old one should be migrated into new one. We need a policy. Paperless. It's good, but it can be worse, right? It can be worse. Enterprise integration, right? Outsourcing, subcontractors, customers, part suppliers. You need to have a more interface than before. Right? Neutral means non-commercial, life cycle, maintenance, 50 years, concurrent engineering, right? More communication, worldwide network, global manufacturing. Structure is divided into three groups. This way. Right. As I said, it's an application protocol. This is for automotive industry, electronics industry, shipbuilding industry, construction industry, process plant is a chemical industry. Right. Each has their own application protocol. Right. Below them, there is a modules. Engines or bolt nut or motors, pumps. Right? Similarly, this is software and standard, so they call this is resources. But among resources, we also have two levels: integrated resources. These are modules. You can say modules. Components, implementation method. This is upside down. So AP is here. Picture is upside down, you can say. Parts 1, 10 series, 20 series, 30 series. There are many standard books. This is language, which describe all these standards. Implementation, how can you implementation? Based on the file, based on database, this is all XML file. This is a text file, XML file, database, implementation method. How can you test whether this is a standard, conformance to standard, ISO? Each nation has their own conformance testing method, right? Your standard, right? Your regulation. Data model. It's a resources. But integrated resources. This is a modules. This is a parts. Module. Integrated resources, parts 40, 50. So I just finished the 57. In our laboratory, we produce a new step parts, 57. New addition to this series, right? And 48 is for feature classes, 48. 100 parts. Application resources, generic and application, and parts library. It is for real parts, but they want to make a standard parts library of all the electronics and mechanical, bolt nut, and hinges, standard. And then more on this ARC, and modules are starting. And at that time, 1,000 series, and there is also module library there. This is standard standard modules and libraries, management system. AP also needs test cases and implementation cases. Complicated, right? Not single simple one. Right? You want to translate CAD file from CATIA to Siemens, you need to have many underlying technologies. That's why they are working for more than 40 years. Right? So this is a sample of Express language. Now they are moving toward XML language. Believe that Express language is better than XML. But why they are moving? Because it's more popular. It is not so good, but still popular. More people are using XML. They believe that. Myself also believe that Express is better language, but only small portion of people are using. So we need to move on to using XML. Schema, entity, subtype. This is object-oriented programming language. Physical file is text file. Real file. Real product, bolt, or box can be represented by ASCII file, text file. Part 21 defines the physical file. Description. Minimal application protocol 214 is automotive industry. Example with a single part. I don't know which part it is. And it is for demonstration. Time is 15 years ago. Rotor client is a person name. Is from a LK Soft company name. He's still coming to the ISO meeting. I will be in that meeting next week in Chicago. I probably meet him. Still, he's coming. He's also operating the company. It was a very small company at that time. Now it's a little bit low. From Germany. He's from Germany. Automotive design, manufacturing design, test parts, that's it. No question. Yes, good.
Professor, what is the, if you want to add some new addition to this step, so what is the driving factor? How do you decide now we have to make something new? Like industry
New standard part. Right.
Can be new part.
New part.
So is it coming from the industry or the staff?
Anyone can do. But it is also proposed by anyone who need. But usually the low level is more theoretical. So 57 is something like a theoretical rather than industrial, right? So requirements are coming from many times from industry, right? But that is more oriented to the application, industry, close, right? But you need also very theoretical part. Right? New technologies coming, say 3D printing, digital twin, industry 4.0, what else, right? AI, or new technology requires new, and also new market. New technology may need a new part here. New industry may need a new part here. Right? So anytime you can raise your proposal, but you need a voting. So participating countries are voting yes or no, right? Discussion and yes or no. Right? Then it can go or not. or not. Right? Very similar, right? Very similar. There is a need you can raise, but you need to make them understand and agree to join, right? Agree to join. It can be an international team to produce a new standard. Because it should be in the internationally accepted standard, right? Not only for Koreans, right? Right.
Who checks the implementation?
Who check, right? Finally, the world should check, right? Industry, the user should check. But in the middle, there is a persons who check. In terms of the baseline is editorial checkers, right? The documentation, but also the software should be tested. Right? That's why we have a testings or the conformance testing, test cases, and others. But usually, I have an idea. I want to propose a new part. Then I also need the implementation myself, right? Because I want to check myself. So then the others, maybe there is an opponent countries. They may have a better idea. So it is competing each other, right? Technology is similar, right? It's a kind of technology, new technology. French may have a better idea, right? But Korea, new technology, one plus. They're competing. So you should show it is working. Then I need the implementation to show that, oh, Bangladesh, you need to vote to me, yes, or not to French, right? Very similar. It is a competition also, competition too. Right? Collaboration and competition, very similar.
My question is with respect to commercial CAD system. Because they implement the step forward, but their step forward implementation is not same.
Right.
So,
right.
What are the things that?
Right. There is a special step. You can check a site. Tax implementers, right. They have a regular meeting to test all the implementers are coming, and there is a test model, and very similar to our test run. Right? So you can visit this site and then see the history and each year they have a 2 round of tests and produce report. No more. Yes? No? Then we can finish. Right?